more complicated one. Before you start collecting and analyzing your data, you want to think about which predictor variables you will need. This obviously typically applies when you collect your own data. And the stuff in yellow here, the experiments are usually somewhat less followed by that. And we're going to figure out why that is. So for a typical survey, you need to go out of your way collecting all kinds of predictor variables. And for an experiment, very often we need not bother so much. Okay, I need a couple of slides to try to bring that argument home. So you have to stay focused for a slide or slide 8 slides or so, I don't know exactly. First, something that I'd like to focus on up front. Okay, this is multiple regression. Not that multiple, you only have 2 predictor variables, but at least more than 1. So let's suppose that we have something here. And suppose that we have something here where the x1 is an experimental variable, something that we did in a lab that we created ourselves. For instance, think about that spider size. So we invite people into the lab and we have, let's say, 12 different sizes of spider. If you come in, then we randomly decide, okay, are you going to get the smallest one, or the slightly bigger one, or one bigger than that, and so on. So we randomly allocate you to a spider size, and then in the end we're going to measure your anxiety by, I don't know, collecting the sweat from your forehead, or who knows what, or we just ask. And then we could try to predict, okay, is spider size a decent predictor for how anxious you are? Okay, you can do it, then still it's not even multiple regression. Now let's assume that we have another variable there of which we think that it might be an effect, have an effect here as well. For instance, age. Let's say that as you get older, you get more accustomed to spiders, and then that effect is smaller, or who knows what. It doesn't matter so much. Now we have 2 variables in there that we need to predict: spider size, we created that ourselves, and age. Okay, so far so good. Now the claim that I want to make here, and that we will need in a minute, is, well, first of all, if it's an experiment, then typically what we're interested in is not so much the effect of age. You may want to take it into account, but we're trying to figure out if this one is working or not. The spider size thing, does that have an effect? So we're interested mainly in only that coefficient, you could argue. And the other thing is, because we randomly allocate these spider sizes to people, it must be the case that the correlation between this one and that one is 0. You know, people are showing up at the lab and you get a spider size at random, so there is no reason for any correlation to be there between the age, between any kind of characteristic, in fact, of the person that comes in and the size of the spider that you get, because it's randomly allocated. Now for the technical bit. We're trying to figure out here, how bad would it be if the real model contains 2 predictor variables, x1 and x2. Normally we do not know the real model, of course. And if I try to estimate that true model based on the true model except for one variable. So I miss one. So the examples here would be, let's assume that this is a real model. Y is equal to beta 1, x1 plus beta 2, x2. And I know here that first of all I'm extracting away from the intercept. There is no beta 0 here. Forget that for a minute. And I'm also extracting away from the epsilon. But let's also not be bothered too much by that. And what we do is we estimate this. So I forget x2, for instance, because I don't have it. And instead, I'm trying to estimate this y equal to, b1 hat, the predicted b1, x1. Now, if I run standard ordinary logistic regressions here, so a multiple regression, with one x, simple regression, then the b1 hat is equal to that. Just believe that. You can look it up in a textbook, it doesn't matter so much, but this is what actually is being calculated behind the scenes. Now let's see. If this is what is being calculated, then that is when we are predicting y from x1. Now let's see what that would give. That gives by putting in there this equation, exactly that. So now we see that the predicted b1 that we would like to be equal to beta 1 actually is equal to beta 1 plus something else. I don't want that to be there. We would be fine if this would be 0. Or stated otherwise, we're totally not fine if this is not 0. Now let's see when that is. This part should be 0 and we are good to go for our estimate to 1 hat. Well, what does it mean that beta 2, if that is not equal to 0, that would mean that x2 is a decent predictor of y. Okay, if x2 is really predictive of whatever the y is, then that beta 2 is not equal to 0. And then we're halfway in the problem. So if there are two things going on, one is x2 is a good predictor of y, and the second is x2 is correlated to x1. If we have both of these, then we're screwed here, because then this term doesn't disappear. Okay, so we were trying to figure out which data do we need here. Well, the answer is basically on the previous slide, because there we saw what we need here is all the variables that have two characteristics. They are correlated with the x1 that we are interested in, and they predict y as well. So if we have variables of that kind, we should include them. Okay, first let me show you that it actually works. I made a toy data set. One y variable and 4 predictor variables, x1, 2, 3, and 4. And I created a model myself here as y is the sum of, and then all this 2 plus 2 times x1 plus 2 times x2 plus 2 times x3 plus 2 times x4 and some noise. Here you see the correlations that I created. And you see here that y is correlated with x1, 2, 3, but not with 4. You see that x1 is correlated with x2, but not with 3 and 4. x2 is correlated with 3 and 4, and well, we argue about whether or not this is a true correlation or not. But again, let's assume that I'm interested in the effect of x1. Now let's see what will happen if I leave out different kinds of variables. First we have x2 over there. No, let's start at the bottom. Let's look at x4. x4 is not related to y, and it's also not related to x1. So that extra term that we had will be 0. It was a product of two things. The left thing is 0, the right thing is also 0, so the whole thing is 0, so we should be fine. Leaving out x4 is not an issue. x3, let's see. We have here x3 is related to y. There's a correlation of 0.44. But it's not related to x1. There's a correlation of 0. Okay, so now I have that term. One of these terms is 0.44, which is not good, but the other one is 0, so the product of the two is 0 as well. So again, leaving out x3 should also not be an issue for predicting the coefficient of x1. And the only one that should be in trouble is x2 here. x2 is related to both y and to x1. So x2 is related to y, 0.31, and to x1, 0.8. So now I have that extra term where there is no 0 to be found, 0.8 times 0.8, and that will cause us some trouble. So let's see. And here we have the results of 4 different regression analyses. Let's first look at the one on the top. I'm predicting y from all the variables there, so I'm exactly using the right model, because I created it in such a way that, that x1, 2, 3, and 4 are indeed predicting y. Now let's see here at these confidence intervals, you'll see that almost all these confidence intervals over there are just fine, and in particular, let's only look at x1 in this case, it is around 2. So if we look at where we are, we have a coefficient of 1.9 and a confidence interval around 2, which is good, because all these coefficients were equal to 2. No trouble whatsoever, but this is still not a good example, because here we are not leaving anything out. Here we have all the predictor variables included. Let's throw one out, x4. x4, we get rid of that one, and what does the model say now? Well, still we have about 2 as a coefficient, which is exactly where we want to be, because the real coefficient is 2, and the confidence interval is nicely around 2. So again, this is fine, sort of working. We now leave out x3, still okay. The estimate is now slightly above 2, but still close enough. And there we again have a confidence interval that includes the 2. So leaving out any of these two, x3 or x4, doesn't matter so much for the coefficient of x1. Finally, this is where the shit hits the fan. x2 was correlated both to x1 and to y. Leave it out. Okay, so leaving a variable out that correlates with another predictor variable that you have in there, and that correlates with your target variable, that is a bad thing, because it messes up the estimates of the other coefficients. So, what does that mean? Well, if you don't want bias in your estimation of the coefficient of some predictor variable, be it spider size or anything else, then what you need is you need all other predictor variables that correlate with that predictor variable that you're looking at and predict your target. So one thing to do would be, if you run a survey and you're say, very interested in the effect of 1x on y, whatever it is in that survey, you need to think about which other variables also predict y and which other variables also predict x, and the ones that do both you should include. And this is also why typically surveys are long, because you have to think about a long list of other things that might also predict your target. And from that list, then check, okay, which one of these might be correlating with the other predictor variable that I'm interested in. And then you might even end up with, well, all. And then in principle, what you need to do is measure all these, which is a bit of a pain in the neck. You get a very long survey because of it. Okay, now, the conclusion of that, well, this is why experiments are so powerful. Think about the spider size example. If I have spider size and I'm trying to predict anxiety, then first I could think about, okay, which other things might predict anxiety? And I could come up with a huge list of other things that might cause you to be anxious. And then from that list, I'll look at, okay, which one of these correlates with that spider size variable that I just created? And the answer would be none. Because the spider size thing is randomly allocated to everybody, and there is no correlation with all the other stuff on the outside. And we need not bother about it. So this is why experiments typically have relatively restricted sets of variables that are being measured. Because the main manipulation that you're interested in is usually randomly allocated across all the subjects. Okay, so let's see that once more. This would be a survey like the spider example again. I'm trying to predict how anxious you get, and I predict this from, let's say, how often you watch Discovery Channel, the number of hours in a week. Because I have the idea that if you see more spiders on television, then you get rid of your anxiety, and then it might be different. That would be survey data. If I'm totally interested in trying to figure out what that E1 is over there, I need to collect all other variables that predict both anxiety and how long you watch Discovery Channel. I get a big survey. If this is the spider size example that I had, and I'm interested in this B1 now, okay, this correlates with nothing else. So for the estimate of that B1, there's no need to bother with lots and lots of other variables. This is why experiments are so strong in method, and why there are so many parts of science where it's difficult to proceed. Because let's suppose that you have a survey, and you try to measure everything there is, and you present what you find, and then always somebody can raise his or her hand and say, wait a minute, I think that there is another predictor for this target variable, and it is the other guy. And you didn't measure it. Well, then there's basically nothing that you can say other than, well, okay, perhaps next time we can include it and see if it makes a big difference, but there's nothing that you can say against it. It would be an experiment if somebody would raise his hand and say, listen, there's another predictor of the target variable that you're looking at. You could simply say, yeah, it might be, but that's not an issue, because the thing that I'm interested in is an experimental variable. It's randomly allocated across my people in the experiment, and every other variable should not bother with that effect.